Hey everybody! The purpose of this video is to give you an explanation of, it's a slight nuance, and before I even start this video I want to make sure you understand something before we even begin this. It's probably going to take like 10 or 15 minutes to get through this. The idea of variation we've been talking about in class is, and the measure we've been using, we've been calling it deviation. We've called it a couple different things. Standard deviation is a very often used term in science, in measurement, in social science. Average deviation is a related term that you all discovered all by yourselves in class, which was totally rad, by the way. They both mean the same thing. They both mean, on average, how far are data points from the average of the data points. So I want to do a recap here in a minute, but I want to make sure that you understand that when I compare average deviation to standard deviation in this video, they both interpret the same way. They both mean the average distance from the average the data points are. Okay, so before, if you ignore the rest of this video, or if you watch it and you're like, I still don't buy what he's selling, just realize that it's going to be easy to get lost in notation, maybe, in this video, and I want to make sure that you don't feel that you should be lost. It's that any kind of deviation we're talking about in this class is going to be the average distance data points are from the average of the data set. Okay, so let's do a recap. These were Ernie's test scores from class that we played with. And after about anywhere between 30 and 45 minutes, I don't remember how long it took, but I kept saying, I want you to measure the deviation. Measure, because you kept saying he's consistent, he's more consistent than Bert. And I kept saying, what do you mean consistent? Give me a number. And eventually you came up with it. Now what you came up with was, you figured out that the average of all these data points was 81. Just like Bert's, and that's what was really upsetting you. But then what you all did was, you came up with the average deviation. And quite frankly, I'm going to throw a formula up here because you deserve it, because you made it up. You all made it up. What you did was, you took each data point, subtracted it from the sample's average, took the absolute value of those. Think about that. You did that, right? You did 82 minus 81 is 1. 81 minus 81 is 0. 80 minus 81 is negative 1. But you decided, if we leave the negatives on, the sum always goes to 0. So you said, let's just drop the negatives. And I said, that's a great idea. Dropping the negatives, that's the function that does that. Once you had all those absolute values, you summed them all up, and then you divided by how many data points there were. Beautiful. Beautiful. And this one, I think, let's see, 2, 0, 1, 2, let's do 1, excuse me, 1, 0, 1, 2, 6. This for Ernie, his average deviation is 1.2. That's what this is for these data. 5 here, and then 1, 0, 1, 2, and 2 added together give us 6. 6 divided by 5 is 1.2. So the way we interpreted this is again a recap from class. The way we interpreted this was, this is the average distance that each of these points is from that average. Perfect. And that's, I love the name average deviation, because literally that's exactly what it means. Now, I also mentioned to you that statisticians generally don't use this measurement. I'm going to give you an extraordinarily technical reason that might not make a whole lot of sense, and that's totally fine. It will make sense if you've had calculus, but if you haven't had calculus, it won't make sense. And then I'll explain to you what measure is used and why. And you might not like that one either, but we'll get around to that. So if you look at this function, this summation of the absolute value of x minus x plus, you realize something, that there's a variable in here. The variable is x. So at the end of the day, this whole thing just becomes the absolute value of x. I mean, it's really based around the function, the absolute value of x. Now you might remember, and you might not, and that's okay too, but you might remember that the absolute value of x function looks like this. Now you can shift that left and right with this multiplier, and that'll move the point left and right. But the big thing to remember right now is there's a point right there. where it switches from negative to positive. And I want to leave that hanging up on the board there for a moment. I want to come back to it. Okay, I'm going to fill the rest of the board with some other stuff. Now, this is average deviation, and it's wonderful. I'm going to put a line right here. We're going to come back. Now, what is more often used in computational statistics, analytical statistics, is something called standard deviation. And here's how it is born. Okay, so standard deviation, remember, it has the exact same meaning. It's the average distance from average. The way it varies from average deviation is how we deal with the negatives. The whole problem, the reason we had to bring the absolute values in was because those negatives and the positives combined together to give us a problem. All the differences zeroed out. Here's how standard deviation deals with it. We start with the data. 82, 81, 80, 79, and 83. Okay. We do exactly the same starting move we did for average deviation, because that's at the base of what we're doing. You're taking the distances from the data points to the average. That's the whole idea. So this is going to be 1, 0, -1, -2, and +2. So right here, same problem exists. If we were to try to average these positions, it averages to 0. And it doesn't matter what data set you have, they're always going to average to 0. Okay, so far so good. Average deviation took the absolute value of these numbers. Standard deviation doesn't. Standard deviation squares these. Now I'm going to put a bug in your mind right now. This function compared to this function. This function here is the quadratic function. You might remember this from previous math classes. Quadratic functions don't have that point right there. They are shaped like this. You might remember, it's called a parabola. You might not, that's okay too. But it's parabolic. It's got a beautiful little smooth bottom that curves uniformly. Okay, we're going to come back to that in a second. Those of you that have had calculus before, that'll make more sense. So you take those and you square them. So 1 becomes 1, 0 stays 0, -1 becomes 1, 4, and 4. Okay, so far so good, except now you're sitting there going, why would you do that? That's stupid, because now, okay, so you made them positive, great. But you made them positive at what cost? They're now squared, totally. And in the formula, we are going to take the square root of that to get rid of it. That's the difference between absolute value and squaring. Squaring is a function that we have destroyed the data with. We have changed the unit. Think about it this way. These units are in points. These distances are in points. These are in squared points. They've been destroyed. We need to get the units back of points, which means the square root. These never got ruined. If you take the absolute value of negative points, it becomes positive points, but it's still points. So I'm totally with you if you're upset with the fact that we just did that. We will deal with that. But the first thing we're going to do is we're going to add up all these destroyed data points. We're going to sum up the squared deviations. That's what that little guy right there is called. That's sometimes you'll see it in research articles sometimes called the sum of squared deviations, or just SS. Sometimes it's just called SS. Don't memorize that. But that's what you would get by adding these guys together. So that ends up being 10. Now, again, here's where it gets a little bit techie, just a tiny bit techie. But again, big picture, we are looking for the average distance of the data point from the average. There are two things you can divide this 10 by right now, depending on what you're talking about. The logical choice would be to divide that by 5, because there are 5 data points. Okay, so if you divided that by 5, you would divide this by 5, and you would get 2. And that is completely logical, and it makes perfect sense because there's 5 data points you divide by 5. If you are dealing with a sample and not a population, mathematically, it is more correct, believe it or not, to divide by 4, which is 1 less than 5, in which case you get 10 divided by 4, or 2.5. Now, I hate to pull a Fermat on you, but this board is not big enough to contain the proof of why that makes sense. I do have a proof of that if you're interested. on the enrichment page of the website. But at this point, I run the risk of making you so buried in technicalities that you're not going to care. I don't want you to worry about that. Whether you divide by 5 or by 4, big picture, we're averaging the distance of the data from the average. So just let that go. Let that go. This has a name. We generally call this S squared. This has a name. We generally call this little sigma squared, Greek letters. Again, this is not to freak you out anymore. It's not to freak you out. It's just to let you know that there are 2 different formulas. We generally never use this one because this assumes we have an entire population. So generally speaking, we always use this one. Generally speaking. And what I'm going to do is I'm going to clear a little bit of space over here where it says standard deviation. Now let's put it up here. Let's put it up here. So if you think about the formula we have now done, we took the sum of those squared deviations, divided it by n minus 1, which is what this actually was down here. The reason I'm doing n minus 1 and not n is because this assumes a population, this assumes a sample. And again, if you want more than that, please check the enrichment page of the website. It's right in there, okay? Thanks. But this is squared. In order to get s back to, or excuse me, s squared back to s, we have to take the square root of the entire thing to get it back to s. And that gets our units back. Points squared then becomes points again. Now at this point, speaking of points, you're sitting there probably dry heaving, completely upset, like, oh my god, this made sense. I know it did. And I was so stoked because when you came up with this, I got so excited because you're creating statistics on your own like I have to do from time to time. And it feels good when you do that, right? Nobody ever thinks to do this. And that's okay because that's why we have technology to actually do the calculations for us. But here's what I want you to understand. The reason this is used over this in practice has nothing to do with simplicity. If it did, we'd use this. It has everything to do with the shape of these 2 curves. If you take calculus, and if you don't take calculus, you can just tune this out for the next 30 seconds. But if you've taken calculus, there's something you cannot do to this that you can do to this. And that's called optimize. You cannot take what's called a derivative of any function that has a corner like this in it somewhere. This removes the corner and creates a smooth, continuous curve with no angular changes. And that's why this guy gets used so much in industry, because when we have to optimize, minimize, maximize, whatever, we have to be able to take that derivative. So this one ends up getting used and this one ends up on the back burner. But here's the deal. Essentially, they're the same thing. They're not exactly the same thing. We figured that out in class. Because I think, if I remember correctly, and this is me doing square roots in my head, I think Ernie's standard deviation wasn't 1.2. The square root of that's more like 1.6. So it's not exactly the same. But here's the deal. As sample sizes get larger, they basically become the same number anyway. And you might be wondering, wait a minute, this is so confusing. If they're the same number, why not just use... Because calculus-based statisticians like as much precision as possible and don't like to sacrifice anything due to something called bias. And I'm getting into 244 stuff here. But here's how I want you to make peace with it, okay? This is the command I have built into your spreadsheet. This is the standard deviation command that you'll be seeing time and time again. Notice it's not exactly equal to the average deviation. That's okay. They become the same as n gets larger. And the reason they become the same as n gets larger is this. You probably have forgotten this from your time in algebra class. But when you take the square root of x squared, it's not equal to x. It's equal to x when x is positive, right? It's equal to x if x is positive. But if x itself is negative, you have to actually it has to be negative x, or the opposite of x. So what mathematicians came up with a long time ago was a way to, instead of doing the piecewise split, they simply said this. So the square root of x squared is just equal to x, algebraically. So the square root of x squared is just equal to the absolute value of x. As n goes off larger and larger and larger, the n and the n minus 1 get closer and closer and closer. Yeah, sure. When there's only 5 data points, when you remove 1, you've taken away 20% of the data set. But suppose there were 50 data points and you remove 1. Well, now you've only taken away 2% of the data set. Suppose there's 100 data points and you remove 1. Now you've taken away 1% of the data set. Suppose there's 10, I think you're getting the point. So as n gets larger, the difference between this denominator and this denominator essentially disappears. And you're left with just this and this. Now, it's a bit of a statistical argument and not a mathematical argument because the n minus 1 is being square rooted here. So you're going to have to get some really big sample sizes before they really get asymptotic. But again, I promise not to use big words in there. I went with the asymptotic. Point being, I want to wrap up, finish this video with the exact same note that I had at the beginning. I want you to think about these measures of variation as the average distance data is from the sample's average. And the one that gets used, and the one you're going to see more and more and more in the world is that one right there, the sample standard deviation. The sample standard deviation. We'll talk more in class as we go. We got plenty more time together to talk through this and get questions answered. But that's the one that gets used in the world, and that's the one I want you to know about. Hope this helped. See you in class.